inch. Okay. Now that per square inch, which is in the denominator, it becomes square inch of this quantity inside the square root sign. Okay. Now the inch in here, which is keep uh, keep foot, magiging keep inch ito because of this 12. So keep inch here and inch below are cancelled. Now this keeps per square inch, matitira na lang square inch as a numerator. Okay? Yung keep, it will cancel dito sa keep sa taas. Okay, may keep din sa baba. Okay. Let me show that so that you will appreciate better. So I said that this will be keep inch. Now below, that will be inch times keep per inches squared. Okay? Yung 2 doon, that's squared. Now, this will actually cancel. Cancel inch, and then inch, cancel keep, and then keep. Right? And then this effectively becomes, sorry, equals inches squared. Okay, yung 2 doon, that's squared. Okay, so that if we will get the square root of that, ganyan, di ba? And then you'll end up with an inch as your final, that's your final unit, inch. Okay? Did you get that? Nasundan nyo yan? Okay, good. I'm glad na nasundan ninyo. So, any question for this example?
Sir?
Okay, so for that example, given the MU value, the factored load, the factored moment, the 850 keep foot, okay, we were able to determine D. So therefore, more or less, you have an idea now how much depth is needed for your beam, which is 24 inches. Okay? Now let's look at this example. It says determine the approximate required depth of the cantilevered beam in 7.2 given the following data. You have a live load of 2.5 kips per foot, and then dead load. Now this W, it tells you that this is a uniformly distributed load. Okay, that uniformly distributed load is illustrated with this, no? It's a distributed load. Tuloy-tuloy yan. And then F prime C, that's the compressive strength of concrete, which is 60 KSI. And then we have B equals 16 inches. Now, so what we do here is we first compute for the self-weight. Okay? Self-weight, that is due uh, due to its weight. It says here, guessing how deep a beam will be is a matter of experience. Generally speaking, cantilevers are usually quite deep. When we say deep, the depth is quite large, no? Compared to, let's say, continuous beam. Okay, an example of a cantilevered beam, as we mentioned before, if you've seen yung sa PICC, no? Quite, the beam there is quite massive kasi yung haba niya, cantilevered siya. So that the beam itself is quite deep. And of course, where it is anchored is also quite massive. The column where the beam is resting, it should resist the moment that it induces. No? Okay? So we get the self-weight per foot is easy to find by multiplying the number of square feet in the cross-section by 150 pounds per cubic foot. Okay? So 16 by 32. Dali. Saan natin galing yung 32? Okay. Sinusubukan lang natin yung 32 if it is if it is appropriate. Okay? So 16 by 32 divided by 144. This 144 is just a conversion factor. Then multiplied by 150. 150 is actually the unit weight of concrete. So therefore, the self-weight would be 0.53 kip per foot. Okay? So if we multiply then the ultimate moment, so 1.4 times this 2.5. Okay, it says it's live load. The dead load is 1.2. Kindly correct this. It should be 1.2. It might confuse you because it's a comma. So it's 1.2. So 1.4 times 1.2, this part is a dead load, plus 0.53. And then plus 1.7 times 2.5, you get 6.7 kips per foot, which gives us a design moment of, now, the formula for mu is WU L squared over 2. Now, you'll ask, Sir, saan po galing? Where did we get that formula? Okay, if you have a cantilevered beam, the maximum moment is at the support. No? So at x equal to 0. And the value of that moment is W, distributed load, times L squared, the length, all over 2. Okay? So this cantilevered beam is acted on by a distributed load from the support up to the free end. Okay, so having that, you get mu equal to 657 kip foot. Okay? Now, assuming rho is equal to 2/3 rho max, it enables us to use the graphs. Entering graph C.14 with 657 kip foot, we get a preliminary effective depth of about 27 inches. Okay, this verifies the assumed overall depth or thickness of 32 inch. There should be enough space for reinforcing and the required cover. Okay. Here, our computed MR is how much? Okay, going back there is 657. 657. Let's look at that. This is skip foot 657. This is 700. So 657 is around in here. Okay, let us first explain yung graph. You have graphs here with certain depths of the beam and with the effective depth, okay, given the moment that is acting on your beam, this will be the graphs. No? But in our problem, we have our B as 16 inches. So we will look at this graph here, where it intersects 657, 657, somewhere here. So that's why we got 28. You have to look down in here. Sorry. To look down in here, 28, somewhere here. Okay? So, kung nandito siya 27 point something, you just round it off here. For every grade here, that's 2, 22, 24, 26, 28, 30. Okay, so it's approximately 28. Yeah? Now, the raw, yung pinakita ko before, given yung F prime C and Fy, okay, you are given raw and the value of your R. You can also use this aside from computing. Okay, you already have your formula for capital R. Now, given rho and F prime C Fy, you can compute it using the equation, but you can also use this table. Okay, particularly for the next example. I think we will do this. Okay. Any question for the previous example? Before I
Hello,
proceed.
sir.
Yes. There's a quick question.
Yung sa 32 po, paano po ulit yun? Like, inassign lang po yung
Yeah.
value.
Sandali. Yeah. Yung 32, is a trial value of yung total height. Okay? Total height yon. And then we found that the effective depth is how much? 27. Now, we've said that the total height should not be equal to the effective depth. Now, in our computation, we got the effective depth as 27. Tama? So, we give an extra allowance for cover. No? For cover, when you say cover, from the outermost reinforcement, okay, dapat may concrete pa yan. Yeah, it's around 1.5 inches concrete. 1 inch is how many centimeter? 1 inch is how many centimeters? 2.54, di ba? And then if you convert 2.54 centimeter to millimeter, okay, in millimeter that's 25.4. So 1.5 inch is around how much? In millimeter. That's 37 plus. But in the code, the minimum cover should be 40 millimeters. Okay? So it just said yung 27 and compute, consistent siya on your assumption at 32. Okay? Na-gets natin yon? So there's a part there na you will guess. Okay? It should be consistent. So yeah, guessing how deep a beam will be as a matter of experience. So you will wonder, how can I get that experience? Perhaps after we've discussed this chapter, you'll get a good grasp already of how much initial depth you will assume. And you have guides. No? You will see later on that you will have guides depending on the length of your beam. Okay? Let's say L over 20, L over 25, L over 28. Parang ganun. That will be your assumed depth of the beam, depending on the loading. As I've said, if it is cantilevered, it should be deeper. Mas malaki yung section. If it is a continuous beam, or fixed at the left, fixed at the right, liliit yung section na kailangan mo. When you say liliit ang section, mas maliit yung depth. Okay? Because you will be dealing with less moment. If you use cantilevered beam, you're dealing with greater moment forces. Okay? Kasi walang support sa dulo eh. Kaya lahat ng moment, okay, will be carried by the support in here. Okay? What is the largest moment sa simply supported beam? Ano yung formula natin sa simply supported beam? Sige nga. I told you to memorize that already. Anyone? Just unmute and then tell me. Given W. Sorry, I forgot to mention how it is loaded. So given W, or it is loaded with a distributed load W and given length. Diba WL squared over 8? Okay? So now, if you remove the support sa dulo, so it becomes a cantilevered beam. Now, what is the formula for the maximum moment of a cantilevered beam? Given the same W, given the same length. Diba? WL squared over 2. Yung kanina, WL squared over 8. Now, this time becomes WL squared over 2. So, it's much greater. No? From 8, yung denominator, magiging 2 na lang. So, it's much great. You are dealing with a much greater moment if you convert a simply supported beam into a cantilevered beam with same distributed length. Okay? So, in effect, you will have to provide a deeper beam. Mas malaking section. Kasi, how is that? Nag-double? Nag-double ba? When you say nag-double, yung WL squared over 2 or over 8, you multiply it by 2. If you multiply it by 2, magiging 4 lang yun. So parang magka-quadruple yung moment mo. Because twice mo siyang i-multiply ng 2. Tama ba? It will double and then another double. Kasi multiplied by 2, magiging 4 yung sa baba. Multiply 2 again, magiging 2 yung sa baba. Para maging WL squared over 2. Okay? So that's how moment is magnified if you're dealing with a cantilevered beam. Okay? But of course, you'll be architects, architectural students. Right away, you see the advantage, di ba? If you're dealing with, if you will make your structure cantilevered. Tama? Kasi wala, free yung sa other side eh. And mas maganda siyang tignan. Di ba? Walang block yung sa kanan. Okay, there's already an architectural value if you're using cantilevered beam. But you will have to deal with greater moments. So, mas malaki yung kailangan mong i-provide na strength for your beam. Okay, do you get that? Okay, let's take a CR break of 5 to 10 minutes.